everyone, my name is Anya, and today on Math and Science Concepts, I will be talking about classifying matter. Here I have with me Tuhina.
Hi everyone.
So before we begin, make sure to like, share, subscribe, and hit that notifications bell so that you never miss another one of my videos. So let's begin. What is matter? All the things around us are made up of matter. Matter is anything that has mass and it occupies space. All the matter in the universe is made up of tiny particles called atoms, and then atom is itself made up of other smaller particles called electrons, protons, neutrons. The matter has various states, and they can easily be converted into other states by providing and removing the energy from the matter.
So what's the matter is kind of a question that somebody wants to ask somebody when they want to know if everything is okay.
But in chemistry, we can literally ask, what is the matter? As in, matter can describe the stuff that makes up everything in the physical world, from the rocks and trees outside to the air you breathe, and even you are made up of matter. What makes up matter, and how can the matter around you be so diverse? Normal matter is made up of atoms. Those atoms can be mixed, combined with, and rearranged to form all the matter around you. For example, in the right conditions, carbon can be found as a pure substance in diamonds, graphite, and even nanotubes. But when combined together, carbon can form carbon dioxide in the air, carbonates that make up seashells, plastics that hold your beverages, and even amino acids that make up you.
Of course, the universe would be a pretty boring place if all the matter stayed exactly the same, right?
Yeah, thankfully, this is not the case. Matter is constantly changing as energy is being added to or released from the matter. Sometimes it just changes state or shape as atoms are rearranged. This happens when water boils or plastic is stretched. Other times, the matter is fundamentally changed as atoms chemically combine with different atoms. This happens when fuel is burned or plants undergo photosynthesis. So, as you look around the world with a chemist's eye, you should think to yourself, what is the matter and what's happening to it?
So there's different forms of matter, and those different forms of matter we discuss here in this next slide, right?
Yes, so the five states of matter exist in the universe, and all the matter around us exists in these states. States and phase are the same thing. Mainly three states, that is, solid, liquid, and gas, are widely seen by us all in the universe around us. For example, rocks, marbles, etc. are in the solid state. Water, blood, milk, etc. are in the liquid state, and air, oxygen, etc. are in the gaseous state. The conversion of matter from one state to another is called a phase change. This process occurs when a large amount of energy is gained or lost. Phase change also depends on factors like pressure and temperature. A phase is a form in which a substance exists. On Earth, the different states of matter are solid, liquid, gas, and plasma. Each form of matter has unique properties, including specific heats, melting points, and boiling points. Under certain conditions, different phases can coexist together. There are 8 thermal processes through which matter can attain a phase change. They are melting, freezing, evaporation, condensation, sublimation, deposition, ionization, and recombination. These 8 phases exist under different temperatures and pressure conditions.
So this is the phase change diagram that you have here, and it explains the different processes, right?
Yes. Would you like me to explain it?
Yes, sure.
So the first phase change is freezing. which is the change of a substance from liquid phase to a solid phase. Melting is the change from a solid phase to a liquid phase, the opposite of freezing. Vaporization is the change from a liquid to a gaseous form, and condensation is the change from a gas to a liquid form. Sublimation is the change from a solid to a gas without becoming a liquid at all. And deposition is the change from a gas to a solid without becoming a liquid. Ionization is the change from a gas phase to a plasma phase, which is ionized particles. And recombination is the change from plasma to gas. I will explain this a little further in the next slide.
Right.
So this slide is self-explanatory. As you can see, the first phase, the molecules that make up a solid are arranged in regular repeating patterns. They are held firmly in place but can vibrate within a limited area. So you can see this regular arranged pattern of the molecules. And they have a slight space and gap between them so that the molecules move around just a slight bit. Comparing this to the liquids, the molecules that make up a liquid flow easily around one another. They are kept from flying apart by attractive forces between them. Liquids assume the shape of their containers. So as you can see, here the liquids are flowing around each other, flowing smoothly and easily. And they're bumping into each other fluidly, as liquids do. And there's a little bit more space for them to move around. And they are assuming the shape of their container. So if this container was a different shape, such as this shape, then it would assume that shape, not the shape that it has right now. Comparing this to the gas, the molecules that make up a gas fly in all directions at great speeds. They are so far apart that the attractive forces between them are insignificant. So you can see here they're flying up and down and sideways and downwards. And they have such a big gap between them that the forces are insignificant. Comparing this to the plasma, at the very high temperatures of stars, atoms lose their electrons. The mixture of electrons and nuclei that results is the plasma state of matter. Plasma is the fourth state of matter and can be created on Earth by passing an electric current through a pressurized gas. It is also present in stars, lightning, the northern lights, fluorescent light bulbs, neon signs, plasma screen TVs, welding arcs, and the tail of the comet. Plasma is a neutral substance overall because it has equal amounts of oppositely charged particles, but it can conduct electricity because it has free electrons. So also you can see the charged particles here in the nuclei. So as you can see here, there is this arrow notating the increasing energy. So to explain this, if you add heat energy to a solid like ice, you will get a liquid such as water, simple H2O. And if you added a little bit more energy to that, you would get a gas like water vapor. And if you heated up the gas even more, in some cases, you might get a plasma, which is super cool. So now let's see what Bose-Einstein condensate is in the next slide. So, Bose-Einstein condensate is a state of matter in which separate atoms or subatomic particles cool to near absolute zero, which is 0 Kelvin, negative 273.15 Celsius, or negative 459.67 Fahrenheit, coalesces into a single quantum mechanical entity, that is, one that can be described by a wave function on a near macroscopic scale. This form of matter was predicted in 1924 by Albert Einstein on the basis of the quantum formulations of the Indian physicist Satyendra Nath Bose. According to Britannica, although it has been predicted for decades, the first atomic BEC, or Bose-Einstein condensate, was made only in 1995 when Eric Cornell and Carl Wienemann of JILA, a research institution jointly operated by the Institute of Standards and Technology, or NIST, and the University of Colorado at Boulder, cooled a gas of rubidium atoms to 1.7 times 10 to the negative 7 Kelvin above absolute zero. Along with Wolfgang Kedrel of the Massachusetts Institute of Technology, or MIT, who created a BC with sodium atoms, these researchers received the 2001 Nobel Prize for Physics. Research on BECs has expanded the understanding of quantum physics and has led to the discovery of new physical effects.
This is so awesome. So, where do we need the Bose-Einstein condensate?
So Bose-Einstein condensates have unique properties, making them incredibly important for understanding the quantum world. Usually, quantum effects are only observable at the level of tiny particles. However, BECs are able to demonstrate quantum phenomena on a macroscopic scale. These quantum effects are magnified, making them easier to study and exploit. In research and academia, BECs can help us explore concepts like superposition and interference, key ideas in quantum physics that describe how particles can exist simultaneously in multiple states and interact with one another with waves and particles. They are critical to advancements in fields like navigation, GPS, and sensing, as well as studying quantum properties like quantum interference and coherence, etc.
Great information. Now we will differentiate between plasma and Bose-Einstein condensate.
So, plasma is a highly ionized gas found in stars and other high temperature environments, while Bose-Einstein condensates occur at extremely low temperatures and involve particles behaving as a single quantum entity.
Great.
So let's move on to the next slide. In this slide, we talk about the relationship between phase change and heat transfer. So, when matter undergoes a phase change, heat is either absorbed or released. This process is called heat transfer, and it can occur in three ways: conduction, convection, and radiation. Conduction occurs when atoms or molecules interact with each other. It happens most frequently in solids, but also occurs in liquids and gases. Conduction is when a substance increases in temperature and the atoms or molecules gain kinetic energy and vibrate faster. When these particles collide, thermal energy transfers from the higher energy particles to the lower energy ones. The cooler molecules begin to vibrate more after they encounter the warmer, more energized molecules. This process continues from the warmer area of the material to the cooler area. Heat is transmitted through the surface until it reaches thermal equilibrium. For conductive heat transfer to occur between molecules, they must be in close contact. Conductive heat transfer varies according to several factors. These include temperature gradient, the material's specific properties, the length of the path of heat travel. Different materials transfer heat at different rates. For example, air has a low conductivity, while metals like copper have a high conductivity. These differences inform the design of many materials for everyday use. Examples of heat conduction would be touching the hot stove top or burning your feet on hot sand.
Nice.
So, convective heat, on the other hand, refers to the movement of thermal energy within fluids. Convection occurs due to the bulk of movement of molecules within the liquid, gas, or liquid gas mixture. Initially, heat is transferred between molecules via conduction, but the main heat transfer is via the motion of molecules within the fluid. Convection is very important because bulk of transfer of molecules within the fluid occurs, and it occurs both in gases and liquids and leads to a cyclical effect. Convection is the process of thermal energy exchange in fluids via the motion of the matter within them. Both natural and forced convective heat transfer exists. Consider a liquid warmed over a heated surface. As the lower levels of fluid increase in temperature, they become less dense. The heated layer then rises due to buoyancy to the top and is replaced by colder fluid. The new lower layer then becomes heated, rising and replacing the cooler, denser upper layer again. This causes convection's cyclical effect. Some examples of convective heat transfer are, in the case of natural convection examples, there is hot air rising above a fire, ice melting, sea breeze or land breeze caused by a difference in pressure of air, and blood circulation in warm-blooded animals. Forced convection examples, on the other hand, include air conditioning, car radiators, water heaters or boilers, and convection ovens, as says the name. Radiation heat transfer, on the other hand, is the process of exchanging thermal energy between two surfaces through electromagnetic waves. It can occur when objects are not in direct contact, are separated in space, or when a hot object transfers heat to a cooler one. Examples include heat or light from the sun, microwaves from an oven, X-rays from an X-ray tube, and gamma rays from radioactive elements. Another interesting fact about radiation is that heat transfer occurs via electromagnetic waves. Unlike conduction and convection, radiation does not need a medium for transmission. Solar radiation energy traverses a 93 million mile vacuum to warm the Earth.
So much of interesting information. Now we'll talk about the elements, the different elements that are present.
So the word atom comes from the Greek atomos, which means indivisible. Thus, atoms cannot be broken down further without losing all meaning of identity. Everything you can see, touch, smell, feel, and taste is made up of atoms. Atoms are the basic building block of all matter, including you and me and everyone else you'll ever meet. So, if we want to know about what Earth is made up of, then we need to know a few things about these incredibly small objects. All the matter that you've ever seen is made up of atoms, or atoms stuck together in configurations of dizzying complexity. A chemical element is a substance that cannot be made into a simpler form by ordinary chemical means. The smallest unit of a chemical element is an atom, and all atoms of a particular element are identical.
So the variety we see in matter, the so much of description that you've already given me is truly staggering. Within 10 meters of us, there are examples of matter: hard, soft, clear, plastic, metal, liquid, gas, solid, hot, cold, alive, dead. I mean, dead plants, not dead humans, of course. And the list goes on. How do we explain the different kinds of matter? After 1,000 years of thinking and observing, we know that the explanation that matter is made up of combination of atoms and different elements. Just as the 26 letters of alphabet can spell enormous number of words, the words that everything that you can imagine, the 92 different elements found on Earth can spell an enormous variety of matter, right? And these all matters are formed of different elements which are consisting of different atoms, which is what exactly you're explaining here, right?
Yes, atoms are the fundamental building blocks that make up matter. But not all atoms are the same. We find 92 naturally occurring types of atoms on Earth. Each unique type of atom is an element. All atoms of the same element are similar to one another but differ from atoms of any other element. All atoms, such as oxygen, silicon, and calcium, are examples of elements. Oxygen atoms have a different structure and properties compared to silicon atoms, calcium atoms, or any other element, but oxygen atoms have the same properties as their own. There are two parts to an atom, as we will see in the next diagram that is in the next slide. At the center of an atom is a nucleus made up of two types of particles called protons and neutrons. Protons have a positive electrical charge. The number of protons in the nucleus determines what element the atom is identified as. Neutrons are about the same size as protons, but they have no charge. They determine what is the isotope of the element. Electrons, on the other hand, are much smaller than protons or neutrons and have a negative electrical charge. They move at nearly the speed of light and orbit the nucleus at exact distances, depending on their energy. Atomic mass, I will talk about now. So, because electrons are minuscule compared to protons and neutrons, the number of protons plus the number of neutrons gives the atom its atomic mass. All atoms of a given element are always having the same number of protons, but may differ in the number of neutrons found in the nucleus. Talking about ions, atoms are stable when they have a full outermost electron energy level. To fill its outermost shell, an atom will give take, or share electrons. When an atom either gains or loses electrons, this creates an ion. Ions have either positive or a negative electrical charge. What is the charge of an ion if the atom loses an electron? An atom with the same number of protons and electrons has no overall charge. So, if an atom loses the negatively charged electron, it will have more protons, therefore having an overall positive charge. Ions with an overall positive charge are referred to as a cation. What is the charge of an ion if the atom gains an electron? If the atom gains an electron, there will be more electrons, and an atom will have an overall negative charge. Ions with this charge are called anions. So, continuing, molecules. In the previous section, I said that many atoms are more stable when they have a net charge. They are more stable as ions, that is. When a cation gets close to an anion, they link up because of their different net charges. Positive charges attract negative charges and vice versa. When two or more atoms link up, they create a molecule. A molecule of water is made up of two atoms of hydrogen and one atom of oxygen. The molecular mass is the sum of the masses of all the atoms in the molecule. A collection of molecules is called a compound.
Nice.
Deep dive into the atom and molecules to find what makes each of them unique. Oxygen atoms bond together in O2, or it might be different atoms bonded together, like water, which is H2O. If three oxygen atoms bond together, you get the molecule ozone, which is O3. Molecules can get complex too. For example, the molecule acetone is made up of carbon, hydrogen, and oxygen. Therefore, it is the chemical formula CH3,2O. Why do atoms form molecules? It all comes down to those positively and negatively charged subatomic particles in an atom. If an electron is lost and gained, an atom can become positively or negatively charged, respectively. When this happens, an atom becomes unstable. Well, atoms like balance. Therefore, when an atom becomes negatively or positively charged, they can attract one another and become balanced again. For example, they might share an electron to form a chemical bond. In this slide, we talk about the chemical bond. Atoms stick together because of chemical attraction, meaning that various types of atoms are attracted to each other and come together in a bond. This attraction is created because of the electrostatic force caused by the attraction between electrons and nuclei. There are various types of chemical bonds, including ionic bonds, covalent bonds, dative bonds, and network covalent bonds. The ionic bond is a type of linkage formed from the electrostatic attraction between oppositely charged ions in a chemical compound. Such a bond forms when the valence or outermost electrons of one atom are transferred permanently to another atom. The atom that loses the electrons becomes a positively charged ion or a cation, while the one that gains them becomes a negatively charged ion or an anion. The ionic compound sodium chloride, also known as table salt, has the chemical formula NaCl, which denotes a 1-to-1 ratio of sodium cations to chloride anions. It is a white crystalline substance that is solid. And over here, you can see the chemical equation. Here is sodium, and here is chlorine. Sodium has one extra electron in its valence shell, and it wishes to transfer it to the chlorine. When it does so, sodium acquires a positive charge, and chlorine attracts a negative charge, and so they bond together in an ionic bond. So, continuing, a covalent compound is created when two nonmetals or two p-block elements combine and share a valence electron to complete the octet and establish stability. When two atoms share valence electrons, a bond is formed that is referred to as a covalent bond. According to the Pauling scale, the bond formed between the atoms is ionic if the difference in electronegativity between them is more than 1.7. But the bond formed between these atoms is covalent if the difference in electronegativity between them is less than 1.7.
So why is NaCl not a covalent bond?
NaCl is not a covalent bond due to its electronegativity difference. This can be explained as chlorine's electronegativity is 3.16, while sodium's electronegativity is equal to 0.93. Therefore, the electronegativity gap between the sodium and the chlorine atoms is 3.16 minus 0.93, which equals 2.23. According to the Pauling scale, for a covalent bond, the value of electronegativity difference should be less than 1.7. But the electronegativity difference of sodium chloride is 2.23, which is a large difference for a compound to be covalent. This indicates that the bond between NaCl is ionic, not covalent. Continuing, a coordinate bond, also called a dative covalent bond, is a covalent bond or a shared pair of electrons in which both electrons come from the same element. Dative bonds are commonly seen in reactions involving hydrogen atoms. As explained by Butterworth-Heinemann, when hydrogen chloride is dissolved in water to make hydrochloric acid, a dative bond is found in the hydronium ion, as you see in the equation here. The hydrogen nucleus is transferred to the water molecule to form hydronium. So it does not contribute any electrons to the bond. Once the bond is formed, there is no difference between a dative bond and an ordinary covalent bond. A network covalent bond is a covalent bond that connects atoms in a continuous network throughout a chemical compound, also known as a network solid or covalent network solid. In a network solid, the atoms are covalently bonded in a repeating pattern, similar to ionic bonds, but held together by covalent bonds instead. This means that there are no individual molecules in a network solid, and the entire crystal or amorphous solid can be considered a macromolecule. Network covalent bonds are generally stronger than ionic bonds. Some examples of network covalent bonds and solids include diamond, which is a pure form of carbon with a repeating series of rings and strong bonding between carbon atoms in all directions. Diamond is one of the hardest known substances and melts above 3,500 Celsius. This is diamond right over here. And you can see that network solid framework. And graphite is another network solid. It is the most stable form of carbon, consisting of sheets and carbon atoms that are covalently bonded together and stacked on top of each other. Graphite has a high melting point, similar to diamond, and has a soft, slippery feel. It is used in pencils and as a dry lubricant. Here you can see its layered pattern as a network solid. Diamond and graphite are both allotropes of carbon. In diamond, each carbon atom bonds to 4 other carbon atoms, whilst in graphite, each carbon atom bonds to 3 other carbon atoms. Thus, diamond bears more of a tetrahedral structure, whereas graphite takes the form of layers. The presence of layers means that atoms can slide over each other easily.
Awesome. This sounds great, Anya.
So, moving on to the next slide. With that, we will take a break and end this presentation here. But before we do that, let's take a look at the visual here. Created by Professor William F. Sheehan at Santa Clara University in 1970, this chart takes the elements, unusually shown like this, and scales them to their relative abundance on the Earth's surface. In the small print beneath the chart, Sheehan notes the chart emphasizes that in real life, a chemist will probably meet oxygen, silicon, and aluminum, and he better do something about it. You got it right, people. So come back and see me in my next presentation where we will talk about the periodic table on my channel, my podcast, for free on YouTube. Do not forget to like, share, subscribe, and hit that notifications bell for more informative videos on math and science concepts. Bye!